In this video, we're going to look at how we actually produce the gradient function from an original function and make sure that we can apply the rules to any polynomial. So to recap from the last video, finding the gradient function is called differentiation. And we looked at the rule to get from the function to the gradient function, and that is looking at each term separately, multiply by the index number, so that's our power, so bring the power down in front of the x term and then subtract 1 from the index number. So we've got two ways we can show that we're describing a gradient function. So if you remember, if the function is given as y equals our gradient function, we can show we're finding the gradient function, we call it dy by dx. But if we are given the original function in function notation f of x, then in that case we show we're finding the gradient function by using the notation f dash of x. So in this red box here we have the rule that we have to apply kind of in words as we are going to think about it in our heads. If we just have a quick look at, in general terms, in general notation, how we find the gradient function each time. If y is x to the n, then to find the gradient function we bring the power down in front of the x and take 1 from the power. So if y is equal to a, where a is some constant x to the n, we still bring the power down in front, but we multiply it by that constant and we still reduce the power by 1. If y equals c, where c is just a constant number, well, that's the equation of a horizontal line, so the gradient dy by dx is always going to be 0. If y is equal to k, where k is some constant times x, well, we know that that's going to be a straight line where the gradient is just equal to the coefficient of x, so dy by dx is simply k. So the wording in the question, we could be asked to find the gradient function, we could be asked to differentiate, we could be asked to find dy by dx, we could also be asked to find the rate of change of y with respect to x. This all just means we're going to use the rule differentiate to find the gradient function. Right, let's just have a look at some examples which you can copy down onto your notes sheet. So first one, y equals x to the 7. Find the gradient function. Well, dy by dx will just equal 7x to the 6. So bring down the power, reduce the power by 1. The second one, y equals 5x to the power of 4. Find dy by dx. Bring down the power of 4 and multiply it by the 5. That gives us 20x, reduce the power by 1 cubed. Number 3 then, we're just going to look at each term separately. So dy by dx equals, well, the first term, if I differentiate, I'm just going to get the 7. Second term, bring down the 3, multiply it by the 6 to give 18. X, reduce the power by 1 squared, and a constant number, well, the dy by dx, or the gradient of the constant number, is just 0, so for that one my gradient function is just 7 minus 18x squared. What I'd like you to do now is pause the video and have a go at these questions in the Further Maths textbook, which you can also find a scan of on Teams in files. So you should have finished those questions now. So what we're going to do is have a look at a couple more examples where we have some algebraic fractions for some of our terms, as we see here with the 4 over x. Now, in order to differentiate this term here, where we've got 4 with x on the denominator of a fraction, we've got to rewrite that fraction in index form so that we can apply our rule for differentiating. So before we start to differentiate, we're just going to have to do a bit of manipulation on the original function. So all the terms are staying the same apart from this 4 over x, which writing in index form gives me 4x to the minus 1, and then my minus 2 on the end. So now I'm ready to differentiate, and I'm going to do each term in turn. So that's 12x squared minus 10x plus 6. Now we'll just be a little bit careful with the signs here. So I'm going to bring down the power, which is minus 1, and multiply that by this minus 4. So I'm going to get a plus 4 there. X to that reduce or subtract 1 from the power, so that's going to give me a power of minus 2. And when I differentiate minus 2, I get 0. So that's my gradient function. We could rewrite this gradient function by turning the negative power back into a fraction, which would look like that. Remember that 4 is the multiplier, so it stays on the numerator. But unless the question asks you to, or it's a show that question asking you to, you can just leave your answer like this line here. So one more just to have a look at then. So here I've got f of x equals 3 over 4x cubed. So again, the first thing we're going to have to do is to rewrite this algebraic fraction as a negative power. Now remember, this 3/4 is just a number, and we cannot change that number, so it stays as 3/4, and the x, in order to bring that up to the numerator, that's x to the minus 3. So we get 3/4 x to the minus 3, which is the same as just having 3/4 in the front of x to the minus 3. So now to differentiate, so my f dash x is going to be, so I need to bring the power down, the minus 3 down, and multiply it by the 3/4. So that will give me minus 9 over 4 x to the minus 4. And again, if I wanted to put that back in its fraction form, that will be minus 9 over 4x to the power of 4. So when we are going between the fraction form and the negative index form, it's just the x that's moving between the numerator and the denominator, because it's only the x that has the power applied to it. The numerical part, the numerical coefficient, stays the same all the way through. Now you should be able to complete exercise 8A from question 4 onwards.